Thank you so much. Thank you for all for being here. I'm going to be talking about temperature programmed desorption of irradiated low temperature ice as analogous to PSR regions. Next slide, please. So just a little basis on experimental conditions that we're working with here. So we are doing cryogenic deposition of deuterated water and then doing methane deposition on top of that deuterated water, as well as doing deuterated water deposited on methane and then another layer of deuterated water on top. So we're going to be working at cryogenic temperatures here to create at about 14 K to create amorphous solid ice. Because at these kind of temperatures, what you get is you actually get a less dense form of ice. So you have pores, which can then contribute to the trapping of volatiles, which is the main focus of this work. We're looking at about a 15 to 30 monolayer thickness of these base water ice shells. That allows for our 100 EV electrons to penetrate almost the entire ice, and so we can create a really nice pore layer there. And then we're using quadrupole mass spectrometry to measure our thermal heating. So what we do is we deposit at 14 and then increase the temperature 2.5 degrees Kelvin every minute and slowly ramp up while continually monitoring the volatile release from these substrates. So as I said before, we're going to have deuterated water that is both irradiated and unirradiated. Then we'll have methane deposited on deuterated water, and that deuterated water will be either irradiated for 30 minutes with these 100 EV electrons or no irradiation. And then last, we'll make our what we considered our methane sandwiches. Next slide, please. As you can see here, with the orange being our irradiated species and the green being our unirradiated species, that with irradiation, we have the production of D2. Makes sense, that's what we've seen before. And we have increased trapping of our D2 that we're producing in these pores with irradiation. So with our plain deuterated, unirradiated ice, we have loss of D2 at about 20 degrees Kelvin, which is what you expect with these kind of conditions. But with irradiation, we're creating these pore vacancies, which is increasing the trapping of the D2. You'll also notice that we have a slight peak at that of carbon. And we think what's happening is that we have CO2 that is co-depositing due to our vacuum limitations. We're at about 1 e to the minus 9 into the high e to the minus 10, so we have a slight amount of CO2 still present. And so that CO2 is then dissociating in our RGA and producing this carbon feature. Because if you notice, we don't really have a methane signal that we would expect. And that 16 peak that you're seeing is the dissociation of the CO2. Next slide, please. So as you can see here, we also have increased trapping with irradiation of our CO species and our CO2 species. So these pores are not just trapping species that we're creating, they're also trapping species that are prevalent in the ice pre-irradiation that is within the ice mixture and is actually co-depositing with our D2O. Again, those two peaks, that first peak of that 28 is our nitrogen peak, and then that second one is the CO2. Next slide, please. Here we're looking at our methane on top of deuterated water. Our first thought was that with this methane on top of deuterated water, you'd maybe have some chemistry occurring and also increased trapping of the methane, but it seems like the two inert species, even with these increased pores, is not increasing your methane trapping. So you have similar systems where you're having that D2 coming out, but you're not getting the trapping of the methane species, and there's no methane irradiation in these set of experiments. Next slide. So again, increased CO2, even with our methane system, doesn't seem to stop the CO2 from trapping, still having that secondary volatile lease trapping at about 80 degrees Kelvin, where you're getting that phase transition of the ice from its amorphous solid water into different phases, which is causing this pore collapse and thus releasing those volatiles. Next slide, please. So this is what I think is the interesting part of this, is this methane sandwich. So this is deuterated water, methane on top, and then deuterated water again. Originally, we were expecting that with the irradiation of this top layer of deuterated water, you'd actually increase your loss of methane because now you've created pores on top. The methane can intercalate through as it heats and then be released. But we actually didn't see that. We still saw increased trapping of our D2O even when it's just the top layer that's been irradiated. And in this system, because we did a thinner layer of deuterated water, we also had a bit of methane irradiation. So you get some interesting methane chemistry that you can see occurring. Next slide. So here what we have is we have intercalation of methane and deuterated water. So you have this 33 peak, which is exhibiting, and you actually have a decrease in your 32 peak. So the O2 that we were seeing earlier, which is probably reminiscent of just within our chamber pre-irradiation, is that's then changing and combining and forming these methylated species even with limited methane irradiation. So we're creating these active species and we're having this increased trapping with irradiation of these volatiles. Next slide, please. So in summary, increased deuterium trapping with irradiation. So we have the production and retention of D2 with irradiation in these instances. And why this really matters is, as we talk about sample return, as we talk about in situ resources, if you're not staying below this pore collapse level and you're not keeping your temperatures cold enough to maintain pores, you're going to lose your volatiles. So we always talk about how you're going to lose hydrogen gas at 20 K, but with irradiation, you can maintain that hydrogen gas in lunar samples to almost 85 K. So that now becomes into a realm where we can look at these volatiles that are occurring on the moon and that are trapping that previously we wouldn't be able to. So the two ways you can push this is, do you say, okay, when I'm bringing samples back, I have to keep it cold. I have to keep it at this 40K to 50K range. Or do you look the other way and say, okay, I need in situ measurement. I need a mass spec. I need something when I'm pulling these samples from the moon, when I'm pulling from these PSRs, when I'm looking at my in situ measurements. Do I need in situ? Do I want to see what's coming off immediately so I can do resource stuff, so I can look at this pore collapse and basically allow it to thermally equilibrate with constant measurement with in situ mass spec? Next slide. So the future work we're looking at here is to the inclusion of anthracite. So basically similar setup where we're drop casting and then irradiating our anthracite as a simulant and an analog, and then depositing and see if we can create these pores and these trapping mechanisms. And then also, how do we stick our D2O to these anthracite samples pre and post irradiation? And does that change the trapping mechanism? Is the increased charge or the different binding sites that you now have on not using a gold substrate change how the pores collapse and how the pores trap? There's also further work going on at Georgia Tech by a colleague of mine who's looking at this sort of intercalation and how these trap. And so some of that work is how can we do a comparison to the computational work that's already being conducted that we can study. We also have the capabilities of adding in some different spectroscopic methods. So trying to measure Polyny-Wagner plots off of these species for understanding the kinetics of this binding. Is it a charging bind? Is it just trapping? Is there kind of a bubble formation that's happening? And what is the dependence on the species that's binding as well with this pore collapse? Thank you.